Well, it's time for another mini lecture to give you a little more information from this nuclear chemistry discussion for those of you who'd like to take advantage of it. Since we were unable to finish all of the critical thinking questions in class today, I thought it might be worth giving you a little more discussion on a couple of these. We left off talking about number 15. If you read the chart on this page, we described that there would be 7 half-lives until there was less than 1%, meaning zero point 0.2 grams out of 20 grams is less than 1%. And so less than 0.2 grams took 7 half-lives. T1 half is called a half-life. So how many days would that be? Well, 7 times 8, 8 is the half-life, is going to be 56 days. What happens to that iodine that is lost? We have to think back to what the decay products were. Effectively, then, the iodine is decaying to make a beta particle, and the remaining atom is converted to xenon because you had 53 iodine turning into 54 xenon. Xenon is a gas, no big deal. And, well, it's just what it does. It turns into that gas. So the next question asks you to predict when all of the radioactivity from iodine will be lost. Many of you caught this in class, I think, and the answer is never, because you will always be having half as much as you had before, but that means you don't ever get to zero. It'll be small, but it will never all be gone. So the next question is asking us about a different isotope, cobalt-60, that has a different half-life. 5.3 years, and the question is approximately how many grams of radioactive cobalt would be left after 11 years. So what you have to think about is you have 100 grams, one half-life elapses, and then you will have half as much, so that would be 50 grams, right? Well, my tool doesn't write today. And 50 grams, but then if you want to have 11 years, that would be effectively about 2 half-lives. So in other words, 5.3 years for the first decay portion, and another 5.3 years for the second decay portion. In other words, you'd have about 25 grams after 11 years. 11 years is just, again, approximation here, but approximately 2 half-lives gives you that amount. The remaining questions on here are not too weighty. The first one, number 19, asks about half-lives of uranium and iodine. The half-lives are very, very different. Iodine-131 is 8 days. Uranium is 10 to the 9th years. Which is more appropriate for internal usage? Well, as you may have guessed from the discussions in class, the one that's more likely to be used for internal purposes will be the iodine, because you will eventually have a much reduced amount of it in your system, and so you would not want to have long-term amounts of radioactivity in your body. Using uranium, you would have some there for a very, very long time. The time for it to become very small would be a long time. Hopefully you put some thought into those other questions if you got to them. The exercises at the end are for you to work in your time as you are able. Of course, the answers are all posted on Blackboard, so I'm not going to take time to talk through them at this point. Interesting to see where some of these things are used, however. So take a look at those exercises at your convenience, especially these questions on exercise number 7. These are good ones to do. They're not too hard. And in fact, I'm going to talk through a little bit here. So the first one is radioactive phosphorus, and the particle that is emitted in this case, if you look it up on that chart on the first page of the activity, is something different. It's called a positron. Kind of funny, because its charge is +1, in the nucleus. So that means that it's like an electron, but it's a +1 charge. Very different, something we haven't run into before. That tells you that the atomic number of the other product has to be 14, which is element 14 silicon, and its mass will not have changed because this thing has effectively no mass, so it's a positively charged something like an electron. Very weird. And that would be 30 silicon 30. The other one here with beta decay for silver, you have to remember the symbol for the beta decay, so it's 0 over -1 E. It's like a positron, but this one's negatively charged, so this is something we're familiar with. Yes, it's an electron. And as in the example with iodine, the mass number won't change, so it'll still be 113, and the atomic number is going to go up to 48. And if you get out your trusty periodic table, I'm pretty sure that was cadmium. All right, last one. If you have gamma and alpha emission here, what would this process be? So alpha, you have to look it up if you didn't remember. It's the 4 over 2, namely a mass of 4, charge of 2, helium. It's literally a helium nucleus without electrons. The gamma particle is shown here with no charge, no mass. Again, as you noted earlier in another question, it doesn't really affect the balancing of the equation to put it in there because it doesn't affect masses and charges. So we have to decide then what the initial particle was. If you look at the atomic numbers, this one must have been 88. And so what is element 88? It is radium. Look it up on your periodic table. Trusty thing to have for these questions. And the mass will have to be the sum of 222 plus 4. That's 226. So that's how you do this kind of problem. Not too bad. Not tricky math. Okay, so recall as you think about these questions how half-life works. Half of it is gone after each half-life. So 1 half-life, half is gone. 2 half-lives, another half is gone. You're down to 25%. 3 half-lives, half of that again. And it looks close to 0 when you get out here at the end, but it's never really quite 0. One thing to comment about that's worth looking at, if you've checked your textbook on this chapter a little bit, you'd run into this. There's a graph that shows how the number of protons for various isotopes compares to the number of neutrons, and which ones of these are radioactive or stable. The stable ones are the blue ones. And the ratio, that when you have the non-radioactive elements right through the middle of this graph, is where there's approximately the same number of neutrons as protons. And so essentially equal numbers of protons and neutrons will give you a stable isotope, as long as you're looking at lower atomic numbers. It doesn't hold very well with heavier elements, but that's one way of making some generalizations about which elements happen to be stable. There are obviously, from this chart, quite a few radioactive isotopes for each of these elements. We're looking at elements from 1 up to 18 in this chart, so lots of different possibilities exist. They may not be abundant, but they're out there. So let's look at some more balancing of these radioactive processes. If they're beta emissions, like it was mentioned in class, essentially a neutron is being turned into a proton plus an electron. So the beta particle is what each of these is going to have. So 0 over -1 in front of the E. And that tells you that the mass number is going to be unchanged. So we'll have 14 in this case. The atomic number will be 1 different. Well, recall what carbon is. Carbon is 6. And so this one better be 1 more. In other words, it will be 7, so that's nitrogen. You've seen this example already, perhaps in class. Another one with a beta emission is hydrogen 3. And so if you have that emitted, what results? The mass is 3, and the atomic number of hydrogen is 1, so now we'll have an atomic number of 2, which is helium. Not ordinary helium, but it is helium. Polonium. If that's a beta emitter, what will you get? Well, 0 over -1 electron E thing with, well, the mass number was, oh, now you have to get out your periodic table to do this one. So your easy reference guide tells you that polonium is element number, would be 84. So write that one in, and that'll help you deduce the product. The other product will be then atomic number 85. Mass is unchanged, so it's 210. Atomic mass number 210. Element 85 is astatine. AT. Not one you probably run into very often. It's the last one in the halogens. All right, strontium. That's another interesting one. Strontium is element number 38. And so if you're looking at strontium as a beta emitter, Then you'll have 0, -1, and E, with the second product being, again, we'll gain 1 in atomic numbers, will go up to 39, and the mass number will be 90. So what's element number 39? Find your trusty periodic table, and it is an interesting one, yttrium. Not one you've run into very often. Okay, let's leave the last two for you to do because I'm sure you can do them. Hopefully you've done these and gotten some practice. So the other kind of problems that you will run into on your homework that I might need to talk you through that you'll be glad for is to do some dosage questions. And here's one about technetium. Technetium is a radioisotope. It's used in various kinds of medical applications. One of them is here described as a guided surgical biopsy of a bone cancer. The patient needs to get an injection of a certain amount, and this unit here is called millicuries, but you don't have to understand it. A certain number of hours before surgery. If the activity of the solution has this many millicuries per milliliter, it's really only a concentration, what volume needs to be injected. So think a little bit carefully here, and you'll recognize that what we're looking for is a way we need to figure out how to get this many millicuries with the solution provided, and the unit is only a unit conversion problem. Start with the one that's not a conversion factor, the 20 millicuries. Just write them down for the way it's shown, it's all right. And then we'll use the concentration of the solution as our conversion factor. One more variation on conversion factors for you. And so 18 millicuries per milliliter. Setting it up correctly, the millicuries will cancel, and then it becomes a calculator exercise. I'll let you fill in the blank to decide what the answer is, but it's only milliliters. That's only a calculator exercise, no problem. One that's similar is shown here on the next slide. Sodium-24 is an unusual form of sodium, but it's used in studying the circulatory system, perhaps, and is to perhaps even treating chronic leukemia. Interesting. Given a saline solution with that sodium-24, the therapeutic dosage is shown here to be 180 millicuries per kilogram of body weight. So what dosage do you give to the patient if they have a mass of 63 kilograms? Again, just a dosage and conversion problem. So start with the one that's not a conversion factor, the 63 kilograms. And from there, we'll need to do something to cancel out kilograms. Well, guess what? This one's really straightforward. The kilograms already on the denominator of this concentration, or this dosage unit. So put your 180 millicuries on top, the kilograms on the bottom, allow the kilograms to cancel, and put it in the calculator, and you'll get an answer, and that tells you how many millicuries this patient should be given, and you'll just have to find the dosage or the concentration of the solution that you will be using to make that work. Alright, a few more comments about decay series, because that didn't come up in our conversation in class time. Decay series are rather interesting, but they are a way of realizing how many different products result when you have a succession of nuclear disintegrations from one particular radioisotope until it finally reaches something that's stable. Uranium-238, and uranium is element number 92, is shown in the figure in the textbook. We'll show you on the next slide here. That has a series of decay products, and radon is another one that has a series of decay products. And so all of these give you multiple radioactive emissions when you realize what their various products are. Radon is problematic in our part of the country because it happens to be highly common in background radiation source in just the geology of our region. It is harmful if it accumulates indoors, and that's partly harmful because it's a gas, and it will be inhaled, infecting your lungs, and it has some associated risk of increased risk for lung cancer. Okay, so looking at this radioactive decay process, rather interesting. If I move my little icon, it would help. If you start off with uranium at the top here, this is uranium-238. And uranium-238 apparently decays to make thorium with a mass number of, you can read this chart, it takes a minute to get used to it, 234. Well, if your mass is changed by 4 and your atomic number has gone from 92 to 90, That tells you you must have had an alpha decay. Thorium apparently converts from there into protactinium. Pa is a really unusual one. Most people have not heard of it. Protactinium has one higher atomic number, so you're going from 90 to 91. So that would be characteristic of a beta decay. Without changing the mass, again, the protactinium is converted into a different form of uranium. Again, another beta decay. Same mass, but now we're back to 92 for atomic number. So a series of decays have happened here where we've got beta twice now. So uranium-234 goes apparently next, and this is only because they told you wouldn't know, to the other form of thorium, that has a mass now of 230. So if you lost a mass of 4 and they changed the atomic number back to 90 again, we have another alpha emission to get to that step. And if you're paying attention to this graph, every time you get an arrow with that particular angle on this graph, it's an alpha emission. So thorium turns into radium, which turns into radon, which turns into polonium. Each of those will be alpha decay processes. And that polonium is 218, which turns into lead. And then we have some beta emissions that turn lead into polonium. But it happens two ways, because then a polonium turns into a different lead. Wow, look at all these. So there's a whole bunch of things that you go through that are beta and alpha decays in this series until you finally reach one which is stable, and that is lead. Lead 206, element 82. And lead isn't particularly good for you either. Lead has its other toxicity issues. So you can see where there's a whole range of radioactive byproducts every time you have a uranium sample. And that can be rather complex to deal with. All right, so polonium was implicated as the means of death of a spy in 2006 in London, and it's an alpha particle emitter. And so let's just make sure we can see how to do an alpha emission. So look up polonium again. Don't forget, that's why you have your trusty periodic table. Polonium is mass of 210 in this case with an atomic number 84. If it's an alpha emission, what do we have? Well, let's see. Alpha again was 4/2 helium, and that means the resulting other product would have an atomic number of 82 and a mass number of 206. You're losing 4 in the mass number. So trusty periodic table, what is 82? 82 is lead. So if you a person ingests polonium-210, they're not only going to have alpha emission, which is a high energy particle and can be dangerous all by itself, but lead is also poisonous. Another common application of radioactivity in your everyday life that you might not have noticed or heard about is in a smoke detector. Smoke detectors use this element americium. Americium is one of the non-naturally occurring elements. It's element number 95. And so if we are told, and you don't know until someone tells you, that it emits alpha particles that are part of how it functions, it ionizes the air within the detector conducting a current, and if there's smoke in the way, the current is interrupted and it triggers the alarm. So again, if this is an alpha particle emitter, what are the products? Well, let's see. 4/2 helium, you're catching on by now, I think. And the other product will have to have an atomic number of 93, a mass number of, do the math, 237. And if you find your trusty periodic table, what comes with a mass number of 93 is neptunium. Kind of a funny element. Who knew? If you read the right thing here. There you go. So neptunium, Np. It's up there with uranium and plutonium, the outer space elements. All right, so that would be enough for this discussion just about. I just want you to recognize that these things come up in the news from time to time. Here's another one from December. So radioactivity is all around you. Hopefully it gives you a little bit of exposure so that you have some informed understanding when you hear about them in various contexts. Good luck with your homework. See you in class.